Section 3.1, defining the derivative. We spent a lot of time talking about limits, and all of that was so that we can define the derivative. So let's get started. Remember that when we talked about a secant line, we said that we could use it to estimate the rate of change at a specific point on a nonlinear function. This graph is using a secant line to approximate the rate of change at x equals a. We're generating another point a little bit further down the curve. I'm going to call that point at the value x, the f of x. And if we wanted the slope of this secant line, all we needed to do was use our slope formula that said take the change in the y values and divide it by the change in the x values. Well, if we're using the points a, comma, f at a and x, comma, f at x, then the slope of the secant line looks like the equation that we have at the top right. Change in y on top, change in x on bottom. Now there's another way to look at this. Instead of looking at the x values and the y values, the function output values, for the exact 2 points, since we know that our goal is to take that secant line and turn it into a tangent line, where we allow this top point to move closer down to our anchor point, what we can do is represent that forward point by using a distance. If we start at our anchor point and we add h to it, we get to this forward point. And we like to represent it this way because h is the distance between a and x. And as we let h get smaller, we allow the distance between a and x to get smaller. So for this forward point, instead of x, comma, f at x, we can write that as a plus h, comma, f at a plus h. And then when we allow h to go to 0, we get closer and closer to our anchor point. So that same secant slope that we have on the top right, we can write that using the h notation. And in the denominator, you'll notice that we can simplify the terms just a little bit. These parentheses are not doing anything for calculations. So if we dropped the parentheses, our denominator would just have a plus h minus a. And the a and minus a would cancel each other out. So that would leave us with just h in the denominator. Taking that secant line and allowing the point to move closer to the anchor point so that we can reach the tangent line, we can use that to come up with a notation involving a limit. So if the blue point needs to get closer to the red point, then we can basically say that the x value that went with the blue point, if we let x approach a, the x value from the red point, then our secant line will turn into a tangent line. So to calculate the slope of a tangent line, we take that same expression that we had to calculate the slope for a secant line, and then we add to it this limit. So the tangent line slope is really the secant slope with a limit applied to it. And the same way that we were able to rewrite the secant line using the h notation, we can also use that h notation for the tangent line, again just applying a limit to it. Now something that's really easy to get confused is that we have two separate notations that actually tell us the same thing. Now in this top notation, notice that it's x approaching a, where a is part of the anchor point. In the second notation, we have h approaching 0, where h represents the distance between a and x. So if you have a limit where h is going to 0, then you're not going to see x appear inside of this notation for the secant slope at all. If you have x approaching a in your limit notation, then you should not see h in your secant slope at all. Now that we have this idea that we can calculate the slope of a tangent line using a limit, we can start to answer questions like, what is the equation of the tangent line? So far, we've just looked for the actual slope of the tangent line, but now we can find the full equation of it. So let's give it a shot. We're looking at the function x squared, and we're trying to approximate or find the tangent line at the point where x is equal to 3. So if we are visual and we want to do like a little sketch, the function x squared is a parabola. And at x equals 3, we're maybe right here. So we're trying to find a tangent line that passes through that point. So we're trying to find the equation of that blue line. That's the goal. To do that, we probably need to remember exactly how to find the equation of a line. Two formulas come to mind: slope-intercept and point-slope. Slope-intercept is the y equals mx plus b equation, where b is the y-intercept and m is the slope of the line. Point-slope actually comes from the equation we use to calculate slope. It looks like y minus y1 is equal to m times x minus x1. If we have a point on the line and the slope of the line, then we'll use the point-slope formula. If we have the slope of the line and the y-intercept, then we would use slope-intercept. So we'll see what we come up with. Regardless, we need to find the slope. So if we're looking for a tangent line, the first thing we should do is calculate the slope of the tangent line. That's literally what we just talked about. That is the slope tangent line, where we take the limit. In this case, I'm going to use the limit involving x and a with what we call a difference quotient of x minus f of a over x minus a. To fill this in, I'm going to use the definition that was provided for the function f. So instead of writing f of x for this first term, I'm going to replace that with x squared. And then instead of writing f at a, I'm going to look and see where we're finding the tangent line at, and it's at x equals 3. That tells me that I should use a is equal to 3. So then I want to evaluate my function at 3 for the f of a portion. And then in the denominator, I will have x minus 3. And always remember to carry your limit signs. X is approaching a, where a is 3. I can take this one step further by replacing the f evaluated at 3 with 3 squared, since my function is the x squared function. Now we have a limit that we can evaluate. Taking a look, we see our worst nightmare, which is indeterminate form. This limit, if we try to do direct substitution, we find 0 on top, 0 on bottom, which is unpleasant, but we have tools to fix that. Remember that if we factor this completely, we can remove any kind of factors that are causing the problem. My numerator happens to be a difference of squares. And if that doesn't pop out at you immediately, practice factoring a little bit more, and it will become very obvious to you when you're looking at a difference of squares. Factoring my numerator allows me to divide off the x minus 3, leaving behind x plus 3. And if I plug in 3 for x, the indeterminate form is gone. I can see that this evaluates to be 3 plus 3, or 6. So all of that was to find the slope of the tangent line, and we just found the slope of the tangent line is 6. Remember that to make the equation of a line, we need the slope and a point, either the y-intercept or any point on the line. Now, to find the y-intercept, all we need to do is plug in x equals 0, and we could use the slope-intercept form, or we can generate a point on the line. Now, if I plugged in 0 to find the y-intercept, that would give me the y-intercept down here. Notice that that point does not pass through our tangent line. So if I used the y-intercept, I would actually get the wrong answer here. We want to use point slope so that we can use the point a, f at a. So we need to find that point. This is going to be the point at x equals a, in other words, at x equals 3. If I plug x equals 3 into my function, I get 3 squared, not cubed, which is equal to 9. So the point on our graph is going to be at 3, 9. Both the function and the tangent line pass through that point. So finally, we're ready to use this point slope form where x1 comes from this 3, the point that's on our function and on our tangent line, and then y1, which is 9, the output of plugging 3 into our function. So then we have y minus 9 equals 6 times x minus 3. And although this is technically the correct answer, it's not finished. We want to clean this up the best we can, hopefully getting it into a y equals format. So I will distribute my 6 into the parentheses over here. Then I will add 9 to both sides of my equation so that I have y equals 6x minus 9. That is the equation of our tangent line to the function x squared at the value x equals 3. And if we'd like, we can graph that in GeoGebra to make sure that we did it correctly. So let's go ahead and open up our GeoGebra graphing calculator. And what we want to check is that for the function x squared at the point x equals 3, so what I'm going to do is say at x equals 3 and then f of 3, for this point, which we need to adjust our view so that we can see it, we want the tangent line that passes through that point. The equation that we found was y equals 6x minus 9. And we can see that we nailed it. Our tangent line does in fact pass through that point. It's perfectly tangent to the curve. No matter how much we zoom in, we can see it only shares the exact point A on our function. If we had made a mistake trying to graph this tangent line, let's say maybe we made a sign error or something and we got plus 9. We could tell that the line we found is not the correct line for 2 reasons. 1, it's definitely not tangent to the curve, and 2, it doesn't pass through the point A. So graphing is a great way to check that we have the correct equation for the tangent line. Let's solve that same exact problem, but using the other notation. Remember that we have 2 notations that we can use to calculate the slope of the tangent line. So using the exact same function, x squared, at the exact same point, x equals 3, we want to come up with that same equation for the tangent line, which, remember, was 6x minus 9. But this time we're going to calculate the slope using the other limit notation. This limit notation asks a few things of us. we need to know what f at a plus h is, and we need to know what f at a is. Now remember, x equals 3 tells us that a is 3 for this problem. So really, we're looking for f at 3 plus h, and we're looking for f at 3. And because we did this problem just a moment ago, we remember f at 3 is 9. It's 3 squared. But the f at 3 plus h we have not done yet. So let's go ahead and do that. F of x is x squared. So if I'm replacing x inside of the parentheses with 3 plus h, then I'm going to replace the x inside of the x squared with 3 plus h. And I could plug this directly into our limit notation, but my advice is to try and simplify that as much as possible before we return to that limit notation. So remember that this is actually a binomial squared, which means we need to FOIL this, or we need to remember the pattern for a perfect square binomial. I happen to remember that pattern. It's the first term squared, so 9, plus 2 times the first term times the second term, so 2 times 3h, and then plus the last term squared. So we really have 9 plus 6h plus h squared. So we will take out the f at a plus h in the limit notation and replace it with 9 plus 6h plus h squared. And then we'll replace this f at a with 9. So then our limit, as h goes to 0, looks like 9 plus 6h plus h squared minus 9 divided by h. Now, when you start to do these often, things will pop out at you, and something that I like to point out as a nice check along the way is that if you did your function evaluation at a plus h correctly, then your numerator, anything that doesn't have an h in it, will go away. Notice that we have a positive 9 and a negative 9. Those two things zero out. So then I'm left with 6h plus h squared in my numerator, which I can write in factored form as h times 6 plus h. And the reason I want to factor that is because this also has an indeterminate form. If I plugged 0 in directly, I would get 0 on top, 0 on bottom, indeterminate. But if I divide off common factors, I'm left with the limit, as h goes to 0, of 6 plus h. And if h is going to 0, then 6 plus h is going to like 6 plus 0, or 6, which is awesome because we said that this was going to give us the slope for the tangent line, and we said that in the last way we did this problem, the slope of the tangent line was 6, and we confirmed that was correct on GeoGebra, so beautiful. Math works.